Welcome. This is a presentation on the field assessment of cold climate air source heat pumps that's currently being performed by the Center for Energy and Environment. This presentation was originally presented in August at ACEEE's Summer Study on Energy Efficiency in Buildings. My name is Nicole Kessler. I'm a research analyst at the Center for Energy and Environment working on the air source heat pump project. Ben Shainbauer is the lead engineer on this project, and our other co-authors are Dave Bohack, Director of Research at Center for Energy and Environment, and Marty Kushler, a Senior Fellow with ACEEE. This project is funded by the Minnesota Department of Commerce Division of Energy Resources through their CARD program, and has also received some additional funding from Great River Energy, an electric co-op in Minnesota, and the Electric Power Research Institute. So in this presentation, we'll go over a brief background of cold climate air source heat pumps and what the opportunity is for them in Minnesota. Talk a little bit about the study methodology, including instrumentation and analysis, and then we'll go into some of the preliminary results from the study, talk a little bit about the policy analysis work that's been done by Marty Kushler, and then end with forward work. Air source heat pumps use a refrigerant system to transfer heat from one space to another. The outdoor unit contains a heat exchanger, a compressor, and a fan, while the indoor unit has a heat exchanger and a fan to distribute the conditioned air to your home. In cold temperatures, the air source heat pump will absorb heat from the outside and release it inside your home. And in warmer outdoor air temperatures, the system process is reversed and it works like your air conditioner does. What's different about cold climate air source heat pumps is that they have an inverter-driven compressor, which allows the compressor speed to modulate and increase capacity during periods of colder outdoor air temperatures. Manufacturers claim that these new cold climate systems are able to transfer heat into homes at outdoor air temperatures at and below 0 degrees Fahrenheit. With these technological advances, cold climate air source heat pumps have the potential to deliver energy and peak savings, as well as reduce reliance on delivered fuels. This project focuses on homes that use delivered fuel for heat. In the winter of 2013-2014, we saw a shortage of propane in Minnesota, and delivered fuel became very expensive. The price of propane went up to $4.60 from about $1.70 per gallon. And in some areas, folks were unable to even get propane. When this happens, it leads to the potential for people to compensate with electric resistant space heaters, which can increase the utility load. There is a market for targeting the technology to homes using delivered fuels. More than 40% of homes in the upper Midwest and more than 25% of homes in the Midwest and 47% of homes across the U.S. do rely on fuels other than natural gas for space heating. If we take a closer look at Minnesota, this figure shows that in Minnesota, the areas with the most opportunity are in outstate Minnesota. The metro area, which is the light yellow area, which consists of Minneapolis, St. Paul, and surrounding suburbs, has less than 4% of the homes using propane for its heat source. But as the color on this figure gets darker, the percent of homes using delivered fuels increases, with the darkest color going up to 40% of the district using propane as their primary heat source. Overall in Minnesota, 10% of the households are using propane for space heating. So this is a field study that has 6 sites. We had 3 cold climate air source heat pumps installed for the previous heating season. This presentation focuses on the preliminary results for those 3 sites. The 3 sites discussed today are all ducted systems with delivered fuel furnace backups. The figure shows the location of the 6 sites. We made an effort to get installs across the state. Overall, we have 4 ducted units and 2 ductless units. At the sites, we're monitoring the field performance of the heat pump with the furnace backup, and we're also monitoring the field performance of the traditional system, so the furnace running on its own. In addition to the field study, this project is also looking at how to incorporate the heating energy savings into Minnesota's CIP program, that's the Conservation Improvement Program. And as a part of this, we're working with ACEEE on the policy implications of the cold climate air source heat pumps. Lastly, for anyone not familiar with the Minnesota climate, the state is in climate zones 6 and 7. So, for example, the city of Duluth has over 9,000 heating degree days with a negative 18 degree Fahrenheit winter design temperature, and the city of Minneapolis has over 7,000 heating degree days with a negative 11 degrees Fahrenheit winter design temperature. This is a table of the equipment that we have installed at each site. So again, there's 6 sites total, and the top 3 sites, the sites in green, were installed in time to collect data during the 2015-2016 heating season. The other 3 sites got installed in late spring, early summer 2016, and will be collecting data from all 6 sites through this upcoming heating season. 4 of these systems are ducted systems, and the first 3 I'm going to show you data on later in this presentation. Site 1 is a 4-ton carrier unit with an LP condensing furnace. Site 2 is a 4-ton Bryant unit with an LP condensing furnace. And Site 3 is a 3-ton carrier unit with an LP 80% efficient furnace. Each home was instrumented with a residential HVAC data acquisition system. We're using a Campbell logger at each site to collect data at 1-second intervals. So you can see we're taking power measurements of both the indoor and outdoor units, and we're also submetering the indoor fan. We're monitoring the reversing valve so we know when the unit runs in defrost mode. We've got thermocouples measuring the supply and return air temperatures. We're also measuring the temperature of the mechanical area and collecting temperature data for the conditioned space. Additionally, we've got a gas meter to measure the backup fuel consumption for the furnace. We've taken delivered airflow measurements using a TrueFlow, and we're also collecting NOAA data from the closest weather stations to each of these homes. We're doing 2 different types of analysis using the field data. The first is looking at the annual energy and cost savings from this system. So we're really taking a closer look at the reduction of delivered fuel use. And then we're also doing calculations of the performance for the air source heat pump and the furnace. So we're looking at the coefficient of performance for the system, and we're looking at this on a daily average and also per heating cycle. So next we'll step into talking about the preliminary results that we have for the study. First, we're going to touch on a few different things, including systems design and furnace integration. So the air source heat pumps were sized for the home's heating load, not the cooling load. This typically meant an increase in tonnage or capacity of the system by 1 size. So where a 2-ton unit would cool a house, a 3-ton unit was installed to meet the heating load. And the purpose of this is to take advantage of the heating capacity at cold temperatures. So if you look at the chart, on the x-axis you have the outside air temperature, and on the y-axis is the heating load of the home and the air source heat pump capacity in BTU per hour. The black line is the home's heating load, while the red, orange, and purple lines are the equipment output, and this was based on manufacturer provided data for a 2-ton, 3-ton, and 4-ton unit. If the system was programmed to be switched to the backup, so switched to the furnace, when the heat pump could no longer meet the full heat load of the home, the 2-ton switches over at 19 degrees Fahrenheit, while the 4-ton unit switches over at 3 degrees Fahrenheit. So the higher tonnage means the unit can meet a higher percent of the heat load of the home. If you look on the right side of the slide, the 2-ton unit could meet 60% of the heat load of the home, while the 3-ton is 77%, and the 4-ton can meet about 86% of this home's heating load. So for the 3 units installed, the systems were sized to meet the heating load of the home down to 10 degrees Fahrenheit. The original intent of this project was to integrate the air source heat pump with the homeowner's existing furnace. However, we quickly found out that this is not something that installers or manufacturers would do. The 2 issues that they cited were, one, that the air handler needs to have a multi-stage fan in order to achieve the full capability of the cold climate air source heat pumps. And 2, that the furnace and the heat pump require integrated controls. So we came up with 4 possible solutions. The first would be to purchase a new communicating condensing furnace with the multi-stage fan. The second, purchase a new 80% efficient furnace with the multi-stage fan and integrated controls. The third would be to retrofit the existing fan and furnace controls. While this might be a retrofit that could be developed by manufacturers in the future, it was not practical for our study, and so that option was eliminated. The fourth option would be to install a plenum heater that could meet the full heat load of the home when the air source heat pump could no longer meet the heat load of the home. But this would mean a large plenum heater, and it would essentially eliminate the need for the furnace, which didn't fit the requirements of our study. So we chose solutions 1 and 2. And solution 1 is more expensive than solution 2, so part of the future analysis we will be doing is looking at the cost effectiveness of getting an 80% unit versus a high efficiency furnace. We installed the 80% furnace in the 3rd site because it had the proper venting already available in the home. Alright, so let's jump into some of the preliminary data we have for these first 3 sites. On this slide, you can see the system coefficient of performance versus the outdoor air temperature, and these are daily averages. On the y-axis, we have the daily system COP. So by system, I'm talking about the air source heat pump with the propane furnace as a backup. And these events are heating events only. This chart does not include any cooling data. And then on the x-axis is the daily average outdoor air temperature in Fahrenheit. So for the 3 sites, you can see that below 10 degrees Fahrenheit, the COPs start to level out. This is when the furnace is meeting the heat load of the home. But you can see that in the warmer temperatures, when the air source heat pump is meeting the heat load, in all 3 of the homes, the coefficient of performance is reaching up to 2.5 to 3. On this slide, we're going to look at heating events. So the previous slide was daily average system efficiency. On this slide, we're looking at heating event efficiency. So this is on the y-axis, you have the heating event coefficient of performance, and on the x-axis, you have the heating event outside air temperature in Fahrenheit. And this data is only for site 2. At this site, we had a furnace, a condensing furnace with a steady state efficiency of above 90%. The orange events on this slide are events where only the air source heat pump was running to meet the heat load. So COPs range from 1.5 to 2 at 10 degrees Fahrenheit and 3 to 3.5 when the outdoor air temperature is in the mid-50s. The purple events are heating events that only had propane to meet the heat load. And so for these events, the air source heat pump was locked out, so the air source heat pump wasn't running in defrost. So you can see that most of these events are occurring below 10 degrees. Again, that's because the air source heat pump was programmed to be locked out at 10 degrees. And the event heat cycle for these events is low, between 0.6 and 0.75. The blue events are heating events that include a defrost cycle at some point during the call for heat. So the defrost cycle, or the freeze protection, for anyone who's not aware, is when the air source heat pump is running in reverse to prevent frost buildup on the outdoor unit. So it's actually adding to the heat load of the home, which can drive some of the event COPs down to below 0.5. Next, we'll take a look at the heating event COPs just for the air source heat pump. So on the x-axis, again, we have the heating event outside air temperature, and the y-axis is the heating event COP. The red data is the data for Site 2, which you actually saw on the previous slide. That's the orange data. The heating event COPs for Site 1 for the air source heat pump have a greater spread than they do at Site 2, but it really follows very closely with Site 2, and actually some of it is hidden, especially down in the 10, 20, 30 degree range. A lot of the data from Site 1 is hidden by Site 2. Site 3, we are seeing some lower COPs during the colder temperatures, which we're going to investigate this heating season. But in the warmer temperatures, we are seeing COPs for up to 3 to 3.5 at all three sites, and the rated COPs of each of these systems at 47 degrees is between the 3 to 3.5 range. So now we'll take a look at energy use versus outdoor air temperature. This again is just at Site 2. On the y-axis, you have energy use in kBTU per day, and on the x-axis is the daily outdoor air temperature. The black line is the furnace-only consumption, which occurred when we ran the unit in a furnace-only mode during alternate mode testing. The yellow line is the air source heat pump only consumption, while the purple line is the furnace consumption when it was being used as a backup to the air source heat pump. So each of these three groups of data were fit with a piecewise linear fit, and then that fit was then used to calculate estimated energy and cost savings from using the air source heat pump with the furnace as a backup versus just using the furnace as a traditional standalone heat system. So here we have the preliminary results where we've used the data that was described on the previous slide to calculate annual energy use and costs. This is for all three sites. You can see with the baseline is just using the furnace to heat the home throughout the season, and the cost at each of these homes is over $1,000 per year. When you add in the air source heat pump, the amount of LP being used goes down drastically. You do now have the electric use, but the total cost still comes down. So we're seeing several $100s of savings at each site, with the most money so far being saved at Site 2. If we look at this on a net BTU basis, we are seeing energy savings of between 39% and 65% at the different sites. And propane use comes down drastically, between 52% and 89%. And the 52% is at Site 3, and if you recall, that is the site that has the 80% efficient furnace. You might be wondering right now about payback. Well, we're not going to talk about it in this presentation because we are still gathering data on the incremental cost of replacement for these units. But right now what we can say is we think that this would probably be best for an end-of-life scenario when you are forced to replace your furnace, or for new construction. And we built cheap propane into this model at $1.29 a gallon, so these savings would increase as the price of propane increases as well. Next, we'll talk a little bit about the policy work that's been done by Marty Kushler. So Marty Kushler looked at the policy context for cold climate air source heat pumps in Minnesota. Currently, there is a lack of structure for utilities to achieve delivered fuel savings from cold climate air source heat pumps. There is a fuel switching concern that does exist. So the fuel switching concern is that one utility would use an energy efficiency program to lure customers away from a second utility. But since the only utility in this scenario is the electric utility, and we're not taking any sort of customers away from the natural gas utilities, that should not apply in these scenarios. Additionally, there is some precedent for electric utilities being able to claim delivered fuel savings, and that's through the low-income SIP program. So this does open the door to the possibility of doing this on a larger scale. Marty's paper goes into several suggestions of what a program might look like to support this, but two of those suggestions are, again, one, to do a net BTU analysis to make sure that there are energy savings, and then again to target homes that do not use utility natural gas, focusing on homes that are using delivered fuel or electric for heat. So I've summarized an excellent paper by Marty in one slide, which probably doesn't do it justice. So here's the information on Marty's paper that goes much more in depth on the policy analysis for air source heat pumps in the Minnesota context. If you go to our project webpage, that's mncee.org/heat_pumps, and you look on the right-hand side of the page, you will find a link to Marty's paper. So in conclusion, we are seeing preliminary results that show that the cold climate heat pumps can meet the heat load of a home down to 10 degrees Fahrenheit with some assistance from the backup. These systems are sized for heating, which means they are going to be oversized for cooling. Our preliminary results do show a coefficient of performances for these three units between 1.5 and 3.5. Again, we are seeing some lower COPs for the unit at Site 3, which we're going to further investigate this coming heating season. And we are seeing a 50 to 90% propane reduction, which is really important because it has the potential to eliminate a winter purchase, since a lot of these homes have a 500-gallon propane tank. If you can reduce the amount of propane that the home has to use, then they could potentially purchase propane early in the season when it's less expensive and not have to refuel throughout the season. So we have more work to do on this project. We have this upcoming heating season where we are going to be collecting data from all 6 sites. That's 4 ducted systems and 2 mini split systems we will be collecting data from. We are also going to be looking at changing some of the air source heat pump controls. So we are thinking of changing the lockout point on some of these units to below 10 degrees to see how the system performs below that set point. And then we're also going to be doing some further analysis into the defrost mode and trying to get, again, a better understanding of how that impacts the system performance. Our final report will be available next year at our website at mncee.org on the Air Source Heat Pump project page. Thanks very much for tuning in. If you have any questions, you can reach me at nkessler@mncee.org.